So, in the earlier class we have looked at state chart and program state machines, right. A version of program state machine is spec chart. Now, we will still be in the paradigm of finite state machine based representation. All these state chart and spec charts were hierarchical communicating finite state machines. Today, we will discuss about SDL, system and description language. It is another example of state based representation. It has got our requirement satisfied, that is hierarchy is satisfied in this, concurrence is also satisfied in this. The major difference from state chart is that in state chart our mode of communication was broadcast or shared memory, right. Broadcast or shared memory. In SDL, we will have asynchronous message passing. You know that there can be two types of communication, one is message passing, another is shared memory. So, here we take recourse to asynchronous message passing. SDL was initially developed for telecommunication applications historically, but then has migrated to other embedded system synthesis as well. This is also, by the way, unlike state chart, SDL, since it is using asynchronous message passing, it is also suitable for modeling distributed applications. It is suitable for modeling distributed applications, because here we are doing message passing and asynchronous message passing. Now, I can have blocking and unblocking whatever we want to do, right. So, here is an example of a SDL, but before that let me just mention about the hierarchy in SDL. The hierarchy is at the lowest level. At the lowest level, we will have FSMs. Those FSMs are known as processes here. Okay. And these processes are abstracted in the form of, so this is the lowest level, then it comes as block. A block may consist of a number of processes, all right. Block can be a collection of processes. And then a number of blocks, communicating blocks, give rise to a system, all right. So, I have drawn in the other direction. So, this is the more specific, I mean more granular, then we come down, right. Now, let us have an example of an SDL representation of an FSM. This is the typical FSM that I have. We have already seen this example FSM a number of times in earlier example. So, A to B, the transition takes place on event G and the output is W. From B to C on event X, the output is X, like that. And here from E, we on F, event F, we come back to A with output V. and from E we come to K. So, this when translated into an SDL looks like this. So, my homing state or the initial state is here. So, I am entering A, all right. Here I am not showing any concurrency, it is only one FSM. Therefore, now you see here what happens, that each of these oblongs, these are the states, okay. And this symbol, a rectangle with an input, I mean this arrow inwards is an input and the arrow outward is an output. So, from A on input event G, here input event G, I produce output W and come to the state B. And then from the state B on input event H, produce the output X and go to C, right. From E, you can see that I have got two edges. So, from E on event F, I produce output V and come back to A, and on event from event state E on event K, I do not produce any output and come back to event A. So, this is the translation. So, the syntax in SDL rests on these oblongs representing states, this rectangles with inward arrow as inputs, rectangles with output arrows as outputs, and that is all. So, this is one process. Okay. Now, let us look at how the communication takes place in this case. So, this part is clear. Now, I can have many such processes. Okay. Now, the process as such is designated as an octagon typically, but actually you see whenever you will be working on SDL, you will be provided with a graphical editor and you will be doing it, all those things. So, the time that I will be needing here to draw those, that you can simply select over there, right. So, I can have a communicating scenario, because it is ours is a communicating FSM. So, I will have one process So, let us call it process 1. There is another process process 2, and let us have another process, process 3. Now, the communication mechanism between these processes is through first in first out queues. So, for each process there is an input FIFO, right. For this process there is an input, let us call it Q 1, we will have another Q, let us call it Q 2, and for this one we will have another Q, Q 3. All right. Now, these FIFO queues are potentially infinite in length. That is the assumption. Okay. These are assumed to be infinite capacity, infinitely large. All right. Now, each process will fetch the next signal, like the signals that we are having here, this G, H, I, whatever. It will be fetched from the queue that is marked for this. All right, it will be taken from this. Now, if this signal, something is here FIFO, I will take this. If this is the event that I am looking for example, this one is looking for this event. So, G, if it be G, then the transition takes place. If not, that signal is ignored by that queue. Okay, it reads, it is ignored, except there is a special case where we can save the signal for future use. Now, obviously, when I say it is an infinite large queue, any engineer will certainly ask how is that possible. So, you must understand that this is a modeling concept, that we are not taking into consideration any limit on this, but when you implement, you cannot really have an infinite queue. So, there you really require some analysis to be done on the whole problem to decide on how much memory you need to allocate on this. Okay. That is a job that you have to do, but as this assumption makes my modeling much simpler, because I do not have to block and all those things. Now, so what happens is that suppose process 1 takes some signal from this queue and finds that it enables a transition, and the transition produces an output. Now, that output can be for a particular process. So, it can put that process thing in this queue, suppose it is for Q 3. Similarly, this one will read from this Q 3 and may produce an output into this, so and so forth. Okay. So, that is the way the communication among SDL FSMs are done. Communication about FSMs. Now, I once again would like to make it clear, this is the description of one FSM, one process. Now, there will be multiple such processes here. Now, all these processes will have to communicate among themselves. For that, the communication assumes this, that there is the existence of an infinite queue. Okay. Now, there may be a question whether it is determinate or not, right. That suppose now a situation occurs that at a particular point of time, say here process 1 has put in some data here. Is it visible that is a red color? I do not think so. And Q 2, this process also writes on this, and that is a different token. I am just showing a different token with a different color. Let me put a different shape, that will be much clearer. So, there are two tokens coming over here in the queue. Now, please note that these two processes are asynchronous and the message passing is asynchronous. Therefore, I have got no idea, I cannot say what will be the order in this queue, circle followed by square or square followed by circle. Accordingly, this process 3 will consume from this and take actions. Now, this consumption will be either circle consumption or square consumption is not known. That is the point of non-determinate behavior in SDL. So, if I run it on actually we run it on a simulator, the simulator can show different behaviors for the same input and all of them are correct, right. So, that is a problem on SDL, but that is there for many such FSM things, that is a common phenomenon. The next thing that we will discuss is how do we handle data. Now, here for each process we can declare local variables and with type specified, right. So, let us have an example. Say I can have a block, again graphically, I mean something like this, where we have got the declaration, the space is little less, counter is an integer and maybe other things like date as a string or other declarations here. Now, in my I can also, is it clear, counter is an integer, right. We can use abstract data types also, but say here there is a inside a particular process, inside a process I can say counter is assigned very bad estimation, counter plus 3, right. So, this counter, and then we come and check the value of counter, and just like a switch statement, based on that I can take different paths. This sort of action is also possible. Therefore, I can also put in data over here. We will look at a concrete example of how we can do the data, but the main thing is that we can specify data inside a process. So, we have seen data, we have seen the state representation, we have seen the communication primitive for that, that is a queue, all right, of unbounded queue. Now, next we look at the process interaction diagram. How would the processes interact among themselves? How would they communicate? So, for that, suppose I have got a block. I said that a block is a higher level than a process. So, say I am describing a block. Just as I had in state charts, I had higher states. So, let me call it say a block B1, all right, and there I am declaring a signal. Actually, the notation is something like this, where I say that A and B are two signals. Okay. Now, I have got two channels. I have got two processes. Let us see. Here is one process, let us call it P1, and there is another process, let us call it P2. Now, I have got channels, there are two channels, let us call it channel 2 and let us call this one to be channel 1. Now, I can associate that through channel 1 both the signals A and B can be propagated through channel 1. So, P1 can send through channel 1 A or B, and through this if I just denote that only A can be passed, then I declare it in this way. Therefore, this diagram depicts the connectivity for communication or interaction among the processes, because in SDL the only mode of communication is message passing, and that will be done through channels. So, I have to specify the channels, and also by using local variables I can specify which variables are connected to which channel. That does not mean that all the time the variables are will be flowing through this channel. Whenever P1 sends A, it can send A through this or through this. In order to send B, it will have to send B only over there. So, that is about the process interaction. So, we have seen, let us recollect up to this, what are the things that we have seen. We have seen that we can implement hierarchy as blocks and then processes for the timing. The processes can have local variables, the processes can communicate among themselves using channels. All right. Now, how do we really show hierarchy? Let us have an example where we show hierarchy explicitly. Let us look at this diagram. Clear? It is coming clear. So, I have got a system S. I said that at the top I have got a system S, and that I have got 3 blocks B, A, B, C, 3 blocks, and there are communications among themselves. Okay. Now, processes, now this block can contain processes, and that is the leaf node. Processes cannot contain other processes, okay, because in SDL what is a process? A process is essentially a FSM. So, I cannot decompose it any further, okay, which I could do in state chart. In state chart, that state machine was itself broken down. So, here is a hierarchy, say S is this thing, then S is divided into A, B, C, right, and then B can be further broken down. You see this here is a decomposition of the block B. B can be broken down into B1 and B2. So, that is B1 and B2, and here is an example of their communication. B1 and B2 communicates with C2 and C3. Now, B1 can be further broken down into processes P1, P2, etc. Okay. This is a hierarchy. I am exactly representing. I am representing the hierarchy, which is so essential for specifying complex systems. So, whenever you have to do a real industry level embedded system design, the specification will be so complex, you will not be able to handle that in a flattened manner. Therefore, you have to look at this hierarchy. You can have the details of the system in terms of blocks at one documentation page, and this is also very much applicable for software engineering as well. All right. And then on another page you go and you put a reference and you come to the lower levels of processes and all those. So, hierarchy I can represent. So, what are my hierarchies? The top level is a system, then blocks, each block can be decomposed into processes, and then we have got channels and all those things. Another very important thing that is there in SDL is timers. We have seen timers. In the last class also we specified that timing specification is a very important aspect of any specification of embedded system. So, how do we represent timers in SDL? So, here is an example. timers can be declared locally. So, here is a a process, right, where I have declared a timer t. Again, this notation is for declaration of the local variables, just as I have done the counter, similarly I have done here. Now, what is done here? Now, all these timing events are also kept in a FIFO queue. So, we start here. So, this is the old one, this is also the old one. Here, for example, this is D and I have got, I am in this state. Suppose right now, I have made a transition from C through the event I, producing the output Y. I went to the state D and this is my state D. This is my state D, all right, and this is my state E. So, I come to state D and now event J occurs. Let me go back and find out that diagram. Here we had this diagram. On D, I was waiting for the event J. Now, on event J, I produce Z and go to E, right. So, that one I am now representing as, I am not producing J here. Here I am setting a timer. Look at what is written. Set, that means set the timer now plus P. Now means it will take the current time, whatever time, it can be a relative time, that when it comes to this state, J event has occurred, then it sets the timer T with a value now plus P. That means what? Now, this timer will start counting down and then I come to E, all right, I come to E. So, instead of that action I have set a timer here, I could have done that whatever action was there, that plus setting the timer, and then I come to E. Now, at E,
it is a countdown timer.
Yeah, let us see what happens here. I have set the timer. Now, I come to this, F happens, I take V. If F happens earlier, I will produce the output V and reset the timer. Otherwise, whichever comes earlier, just like a watchdog. Suppose I have said that from now give 20 milliseconds, and this event F does not take place within 20 milliseconds, then this timer will be giving you the timeout signal, and so that is coming as an input and will go to A. Is it clear?
But
so
now once the timer triggers the operation, then it is not reset.
No, whenever the timer triggers, then automatically this timer is reset automatically. Here I am doing it forcibly, right. Here I am doing it forcibly, but when the timer triggers, it will automatically be reset. And reset means again it will be now, it is not active, right, because again when we come through this process, the timer will be set here. It is not automatically set to the now plus P. Okay.
So, what is now exactly?
Now means the exact whatever time, the real time, whatever is the time now, all right. You come to this point. So, from here it is an offset, P is an offset from here this. So, now is a very useful construct that has been used in SDL, where I can fetch the time, current time based on this. I could say if now is greater than this or something.
From where does it get this now?
That is from the global clock that the system will have. The system has got a clock, and from there it will take a value, and then it can make it a relative value or absolute value, that really does not matter in that case. There are additional language elements like procedures. We can add procedures. We can have additional elements, which I am not discussing in detail. we can have advanced data declarations, data structures you can put in, and you can create and terminate processes. Okay. And there has been different varieties of this. Now, the reason of discussing SDL is mainly to show that here in a state machine we can also do it using message passing, all right, asynchronous message passing, and the timers and all those things are a little different. Now, I will conclude. There is also another detailed example that we will do, but let me just show you a simple example. We will do the details later. Say I want to build up a vending machine. Okay. All of you know about the vending machine, and in finite state automata or switching theory, you must have designed some FSM for vending machine. So, here is a little complex vending machine that I am showing here. It is real complex. So, we will deal with that maybe tomorrow or in the next class. So, here is the complete vending machine, that is the system. And what are the blocks in that? The blocks are, one is the coin interface, one is the decoding the requests, whatever requests are coming, what I want to have a Coke or a cookie, a block to provide you the change. So, these are the three blocks, and there are number of declarations. Okay. These declarations will come to later, and along with these blocks there are channels defined. So, I have got a channel through which I can have the coins, and what are the coins? 50 paisa, 1 rupee, 2 rupees, 5 rupees. There is a channel between coin interface and decode request. Whatever I am adding, that will go through this channel add. Okay. And so, it will also have a coin control on this side, and this one is accepting the coins. So, it will, and there is this one is also accepting the request for what you want to purchase nachos, purchase chips, purchase cookies, purchase Coke. All right. This will show you the behavior. Through this, I can also say I want to reload nachos, it is over, reload chips, reload cookies, reload Coke. So, all these are coming through request channel, and based on the request, if the amount has been given, it is also displaying the amount. It is showing whether anything is empty, something that is purchased is spit out, that means given, all right. And if there is any change, it comes to this change interface, which shows the exact display and provides a change. So, at the top level, this is what I have, right. So, here what I am showing? I am showing the blocks. See, although I am just showing the blocks. So, you can look at this and you can understand what it is doing. I am coming to the signals later. Signals are all these data that can come up, all right. These are integers, when I add is an integer, everything. So, this is the block and there are channels there. So, that is my top level. Now, in the next lecture, I will break it down and show how this can be processed further.